Moving on to Chapter 5, we're going to cover mass and energy analysis of control volumes. So here are the objectives. I'm not going to run through all of them. So the conservation of mass, we know that that's the first law, right? It's actually the synonym. So some people say the first law of thermodynamics. Some people say the conservation of energy. Sorry. And so with that, we have a conservation of mass. Mass, like energy, is a conserved property, and it cannot be created or destroyed during a process. Okay, so the first law of thermodynamics is a conservation of energy. So energy cannot be created nor destroyed. It can be transferred or changed, right? And so for the conservation of mass, when you're looking at it under just the starting and stopping point of a process, right, not as a whole entity, we're just looking at it during a process. Mass, like energy, is a conserved property, and it cannot be created or destroyed during a process. Closed system, the mass of the system remains constant during a process. Right, remember we've talked about that? We've got a box. It's unchanging, right? No volume changes, things like that. Control volumes. Mass can cross the boundaries, and so we must keep track of the amount of mass entering and leaving the control volume. Okay, so mass M, energy E can be converted to each other according to E equals mc squared. I'm sure you've all heard of that. And then C is the speed of light in a vacuum, so it is that constant. And then the mass change due to energy change is negligible. And then this just at the bottom shows mass is conserved during a chemical reaction. So you have 2 plus 16 equals H2O, 18. So just showing that there's 100% transfer during that process. Mass and flow volume rates. So we have these definitions here. And just to give you, we start here and then we go down and we go down. The important one, right, is the mass flow rate and then the volume flow rate. And then this is the definition of average velocity, okay? And then the average velocity, V average, or VAVG, is defined as the average speed through a cross-section. So remember, if you have a tube and you're talking about the cross-sectional area, that your cross-section would be here, right? It's the cross-sectional area of it, or here. So this is where you have, half of that or so. So this is a cross-section there. And then here you see the A for the cross-section of the area. The volume flow rate is the volume of fluid flowing through a cross-section per unit time. Because when we're talking about rate, we are in relation to time, right? Miles per hour is a rate. You think like that, and you're talking about it in relation to time. So conservation of mass principle. So it's the total mass entering the CV during a change in time. So during a time period, less the total mass leaving. So it's the same thing. It's just the total mass. I'm a little sick, so it sounds like I'm saying mouse. It's the total mass entering less the total mass leaving, and then you get the net change. Okay, and so then the conservation of mass principle for control volume, the net mass transfer to or from a control volume during a time interval, which is delta T, so the change in T, is equal to the net change, increase or decrease, in the total mass within the control volume during a change in T. So, and then here's some formulas here. So you've got what the change in MCV here, kilograms, and then kilograms again. So we have that, and then we have, I'll refer to this. And when you see the dot up here, that means rate. It's going to be, that's what that means right there. It's the little dot, but you'll hear me call this either mass rate or mass dot in, less mass dot out. And So this is the conservation of mass principle for an ordinary bathtub. So you see you have mass in, which is 50 kilograms, and then you have mass out, and then you have the total mass of the bathtub is 20 kilograms, and so you know just by switching those around that you can deduce that the mass out was 30 kilograms then. And then these equations are often referred to, these three above, as the mass balance and are applicable to any control volume undergoing any kind of process. So this is important to know about these three formulas right here. And then the conservation of mass. So it's the total mass within the control volume, CV, and then the rate of change of mass within the CV, and then normal component velocity. So it's just all of these formulas here. And then the differential control volume, dV, and the differential control surface, dA, used in the derivation of conservation of mass relation. So it's just, this is really important because we can start using liquids to measure not uniform shapes. But we're not really going to get into that. But here you have the general conservation of mass, and these are just, they're just messed up again. Okay. Huh. See, because you're supposed to, oh yeah. Oh yeah, so this is just the thing. Okay. So it's supposed to let you click and go, but it's just not doing that. The time rate of change of mass within the control volume plus the net mass flow rate through the control surface is equal to 0. So that's all that formula is saying. And again, we will work these. So these formulas are not meant for you to take off of this page and go and work. That is a separate video. This is just meant for you to really pick up the terminology and see the schematics and be really just introduced, so that when I start talking about, what a rate is, you will have already talked about it and you already know, like, oh, well, that's dependent on time, even if you're not sure how to calculate it. Control surface at an angle to the flow. So you can see that this cross-sectional area, you see it has the arc here. And so this is at an angle, and then control surface normal to. So when we see normal to, and I have mentioned this before, but we're going to go ahead and talk about it. I want you to think of an XY axis when I say normal to, because normal to is straight down like this. So it doesn't matter what it is, normal to is straight down, completely straight down. That is normal to. Everything else is not normal to, but it's normal to, like you standing on the ground. That is a normal to. A control surface should always be selected normal to the flow at all locations where it crosses the fluid flow to avoid complications. This is exactly what it's for, to avoid complications, even though the result is the same. The control volume should always be selected normal to the flow at all locations. So you don't avoid complications. The result may be the same, but that consistency is an answer, right? And validation. Mass balance for steady flow processes. During a steady flow process, the amount of mass contained within a control volume does not change with time. That's important to know. So during a steady flow process, steady flow, constant, consistent flow process, the total amount of mass contained within a control volume does not change with time. The total amount of mass entering a control volume equal to the total amount leaving, right? Okay, so I want you to think of it just like this, right? So if you have, let's say you just have, 20 in here. Doesn't matter. You have 2 entering in from here, and you have 3 entering in from here. And therefore, as this 5 enters, we have to maintain what's in here. So 5 has to leave. These numbers in and out don't necessarily. Sometimes they do, but that's more for just a coincidence. These ins and outs do not determine or dictate what your control volume is, because you could have a huge reservoir, right? If you have a huge bucket with a little bitty hole here, and you have water dripping out and you have water dripping in, you could have the same flow rate and you could have one coming in and one coming out, but you could have 100 in here. But if this is lidded, and this is pushing one in, then it's going to push one out, because we have a control volume. We have a constant amount of liquid in there, right? But the in and out doesn't necessarily determine, just because you have 5 in doesn't mean that you can only have 5 in your control volume. Okay? And so the conservation of mass principle for 2 inlet, 1 outlet steady flow systems, and then for steady flow system, and that's that diagram that we just looked at before. For steady flow processes, we are interested in the amount of mass flowing per unit time so that we can get that rate information, and that's the mass flow rate, of course. Many engineered devices such as nozzles, diffusers, turbines, compressors, pumps involve a single stream, which is only 1 inlet and 1 outlet, so just one shot straight through, right? So if you have a nozzle like this, right, that's 1 in and 1 out. Or if you have a diffuser, it's the exact opposite. You have 1 in and 1 out, right? Or just a pump, we'll just put a tube. 1 in, 1 out, right? Special cases is, of course, incompressible flow. The conservation of mass relations can be simplified even further when the fluid is incompressible, which is usually the case for liquids, right? So we have steady incompressible, and then we have steady incompressible, which is single flow. There's no such thing as a conservation of volume principle for steady flow of liquids. The volume flow rates as well as the mass flow rates remain constant. Okay, so when we're talking about steady flow, for steady flow of liquids, because liquids it's usually incompressible, the volume flow rates and the mass flow rates remain constant, since liquids are essentially incompressible substances. Continuing with the conservation of mass, during a steady flow process, control volume rates are not necessarily conserved, although flat mass flow rates are. Okay, so when we're talking about steady flow process, we are really concerned about, again, the steady flow, the rate of it. So mass flow rates are conserved, but maybe not so much the volume flow rates. Okay. And so you can see here that the mass going in is 2 kilograms per second, and that's equal to M2. So that's an important one, right? So if I say, hey, you have a steady flow process, and I give you these information and you need the mass flow rate at state 2, well, you know that because you know that the mass flow rates are conserved. They are the same. But maybe you would then need to find the volume, right? Flow work or flow energy, the work or energy required to push the mass into or out of the control volume. So it's the force that you need. This work is necessary for maintaining a continuous flow through a control volume. And so you have force equals PA, pressure and area, here. And then you've got a workflow rate, and that's equal to FL, PAL, PAL, and PV in kilojoules, and then a workflow rate is equal to PV, workflow equal to PV. So you have, and workflow is equal to PV. So you have multiple different ways to get there, just depending on the amount of energy that you would have. So here, if you have, some sort of gas or a liquid here that's expanding, maybe, you've got something, something here that is putting an outward force on it, outward pressure. And then you have a force here, maybe to compress it, right? In the absence of acceleration, the force applied on a fluid by a piston is equal to the force applied on the piston by the fluid. And that's because it's easier to see if it's horizontal, in my opinion, or vertical, in my opinion. So if you have a piston right here, and you have nothing holding up this piston, nothing. Well, what's it going to do? It's going to drop to the ground, right? So if we have, something in here, a fluid, we'll just call it a fluid because it doesn't matter what it is, and the natural pressure of the fluid is 10, then we know that for this piston to remain right there, not go up, not go down, then the natural force that this piston is applying is also 10. They have to be equal because this is staying still. If this was 11, this force would go down. If this was 9, this would go up, right? So they have to be equal. Flow work is the energy needed to push a fluid in or out of a control volume and is equal to PV. So it just talks about the force that we need to move it. Here are some equations. Total energy of a flowing fluid. And so we have E, we have theta, which is the 0 with the line here. This is theta. And then we have the units as well. And then the flow energy is automatically taken care of by enthalpy. In fact, this is the main reason for defining the property enthalpy. So the reason we have enthalpy, which you will work with it a lot, but it won't become as second nature as some of your other properties, is just for the flow energy. So here the total energy consists of 3 parts for a non-flowing fluid and 4 parts for a flowing fluid. So if we have a non-flowing fluid, we have 3 parts. We have this internal energy, we have the kinetic energy, and we have potential energy. So we always have those energies, remember? That relationship between those. And then for a flowing fluid, we have the internal energy again. We have the kinetic energy again. We have the potential energy. Then we also have the flow energy. Okay? And so here we have energy transport by mass. So it's the amount of energy transport, and then the rate of energy transport. So we have those rates. And then when kinetic and potential energies of a fluid system are negligible, E mass is equal to mH, and then E mass, yeah. And then when the properties of the mass at each inlet or exit change with time as well as over a cross section, then you can take this interval down here. But more importantly for the schematic, the product mg qi, so you see here, is the energy transported into a control volume by mass per unit time. So here, I don't know why that's G, why they have that. There it is. Change that to a dot. We give you a rate because we're doing it per unit time. Steady flow process, a process during which a fluid flows through a control volume steadily, right? And so then when we have that, we know that mass in is equal to mass out. Many engineering systems, such as power plants, operate under steady conditions because remember, we need it to run all the time. We need that steady state, like our refrigerator. We need it to run consistently and continuously. Under steady flow conditions, the mass and energy contents of the control volume remain constant. So everything's going to be constant. Under steady flow conditions, the fluid properties at an inlet or exit remain constant, which means they do not change over time. And then here's the information and equations for the mass and energy balances for a steady flow process. And so we will work these as well. And then just to note that some portions of it we will start working, remember? And basically, this is equal, the inlet is equal to the exit. And you'll see work out, some of all of the energies out, work in, some of all the energies in, right? And then here's just some more information. It's when kinetic and potential energy changes are negligible. It's just a little note, but it's really just more formulas. Okay, so the conservation of energy principle, the water stream experiences an increase in its total energy as it flows through the water heater that is equal to the electric energy supplied to the water minus the heat loss. So again, this is just taking into account the conservation of energy in the first law of thermodynamics. Energy is never created nor destroyed, right? So the energy stream experiences an increase in its total energy. Okay, if we have something that is increasing in its total energy, we're getting it from somewhere, right? As it flows through a water heater, that's where we're getting it. We're getting the energy from the water heater. Where's the water heater getting it? That is equal to the electric energy supplied to the water minus the heat losses, because we're going to have some heat loss. So it's just molding how we are getting increases in energy when we're not creating it, because of course we cannot create it. Under steady operation, shaft work and electrical work are the only forms of work a simple compressible system may involve. So this is just a note. Okay? And then the units are joules, kilojoules, because it gives you some formulas there. At very high velocities, even small changes in velocities can cause significant changes in kinetic energy and fluid. So that should make sense, because when you have kinetic energy, when you have that energy of moving, right? So you think of the book falling, when you're holding the book, everything is loaded up as potential energy. And then when it starts falling, if you drop it, it starts falling and the book is moving, then you're converting it into kinetic energy. So of course, if you were to throw that book, right, even though, it may overall be, a little less or not a huge amount of change in the velocity difference, it can cause a significant change in the kinetic energy. And so here it just shows V1 and V2 and those changes. Many engineering devices operate essentially under the same conditions for long periods of time. That's because we need them to. The components of a steam power plant, turbines, compressors, heat exchangers, pumps, they operate non-stop for months before the system is shut down for maintenance. Therefore, these devices can be conveniently analyzed as steady flow devices. That's because that's what we need to. And honestly, and there's a whole industry for this, to make these heat exchangers and pumps and turbines and compressors last as long as possible, and the goal for indefinite. Someone would love to be able to put a turbine in their steam power plant and never have to change it. That's the goal, right? And so therefore we look at those as steady flow devices. A modern land-based gas turbine used for electric power production, this is a schematic for it. This is a GE LM5000 turbine. It has a length of 6.2 meters. That's enormous. Weighs 12.5 tons and produces 55.2 megawatts at 3,600 RPMs with steam injection. That's just amazing. It's such an amazing feat of engineering. So we have nozzles and diffusers. Briefly introduce those. I drew them when we were talking about one entrance and one outlet, one inlet and one outlet. Nozzles and diffusers are commonly utilized in jet engines, rockets, spacecraft, and even garden hoses. So, and nozzles and diffusers, they look the exact same and they are completely opposite. They are the polar opposites. And you can see that because they just are flipped around. A nozzle is a device that increases the velocity of the fluid. So I want you to think of this as your garden hose. With a nozzle, you have a larger cross-sectional area in the hose, right? You have a larger cross-sectional area coming in from the hose, and it's decreasing to a smaller cross-sectional hose. And when you have that nozzle on there, it increases the velocity of a fluid at the expense of pressure. Okay, so V goes up, pressure goes down. Okay, and a diffuser is a device that increases the pressure. So our cross-sectional area is increasing, and the pressure increases the pressure by slowing it down. So velocity decreases, pressure increases. So they're just the exact opposite. And we talked about the cross-sectional area of a nozzle decreases in the flow direction for subsonic fluids and increases for supersonic flows, and the reverse is true for the diffusers, of course, because they are the same. And then here's the energy balance. Diffuser of a jet engine, discussed. So here's the formula here. But it's just the deceleration sorry, of the air in a diffuser. And then the acceleration of steam in a nozzle. So this is just using the nozzle. And you can see how your pressure is going down. So you have P1 to P2 is decrease. But your volume, your velocity has definitely increased, even though we don't have V1 over here. But we do have P2 decreasing. Turbines and compressors. So turbine drives the electric generator in steam, gas, and hydroelectric power plants. As the fluid passes through the turbine, work is done against the blades, which are attached to the shaft. As a result, the shaft rotates and the turbine produces work. So this is just letting you know what a turbine does and how it functions. And if you've seen, a fan, I'm sure all of you have seen them. Compressors, as well as pumps and fans, are devices used to increase the pressure of a fluid. Work is supplied to these devices from an external source through a rotating shaft. So the turbine blade attaches to the shaft and it produces the work. And then the source for compressor, pumps, and fans is the rotating shaft doing work on those. A fan increases the pressure of gas slightly and is mainly used to mobilize a gas. A compressor is capable of compressing the gas to very high pressures, and pumps work very much like compressors, except they handle liquids instead of gases. So you have compressors and pumps, and it's just to handle two different working fluids. Because remember, when we talk about working fluids within thermodynamics, it doesn't have to be a liquid, right? The fluid doesn't have to be a liquid. We're talking about gases, air, and liquids as well. Compressing air by a compressor. And so this just goes into, if you have in and then you have Q out, you have a temperature and a pressure in and a temperature and a pressure out. You see those changing, and it's going into a nozzle, and you have work being done on that shaft there. And you have a mass rate of 0.02 kilograms per second, and then you have some formulas as well. And then here, when you're talking about a diffuser or a steam turbine, you have a shaft going the complete opposite way with work, and you have P1, T1, V1, and Z coming in, and then you have an increase in pressure and a increase in velocity there. So throttling valves are any kind of flow restricting device. So it's going to restrict, it's going to throttle the flow. That causes a significant pressure drop in the fluid. What is the difference between a turbine and a throttling valve? The pressure drop in a fluid is often accompanied by a large drop in temperature. And for that reason, throttling devices are commonly used in refrigeration and air conditioning applications. Because remember, our air conditioner and our refrigerator, those are not normal everyday items. It's not going to happen naturally in world. So we have to come up with engineering items that will achieve that for us. And so that's what we have done. We've used throttling devices because we need that large drop in temperature. Okay, so here's the example of a throttling valve. The temperature of an ideal gas does not change during throttling. H is equal to constant. And then the pressure. And so here we see a throttling valve. And so we see the flow in the brake and the tubing. And so we have internal energy plus flow energy is constant. And during a throttling process, the enthalpy, flow energy, and the internal energy of a fluid remain constant. But internal and flow energies may be converted to each other. So we do have some mixing chambers, and you'll see that in your shower, right? So engineering applications, a section where the mixing process takes place, is commonly referred to as a mixing chamber. So where this cold and hot water will mix, and at that T elbow. The mixing chamber does not have to be a distinct chamber. An ordinary T elbow or Y elbow will work, and it will serve as a mixing chamber for hot and cold water streams. The conservation of mass principle for a mixing chamber requires that the sum of the incoming mass flow rates equal the mass flow rate outgoing, right? So the conservation means that whatever's coming in added together need to collectively exit at the same rate. The conservation of energy equation is analogous to the conservation of mass equation. So mixing hot and cold waters in a shower. So you see you have T1 in and T2. You see the significant 90-degree temperature difference, and you see that that's exiting at 110. So heat exchangers are devices where two moving fluid streams exchange heat without mixing. So that's really important. Heat exchangers are widely used in various industries, and they come in various designs. This is really important when you want to heat something up but not mix it, right? So if you want to mix a hot and a cold water to make warm water, well, then just mix them together, that's fine. But say you need to heat up another working fluid, but you can't, maybe you can't apply a direct heat, right? Maybe you can't, use some kind of work, or electrical thing, and you need maybe just like some indirect contact. Well, then you could have that colder fluid circling around an alloy or a metal tubing that has very hot liquid piping through the middle, which will in turn exchange heat, warming up the fluid. And so you see here, you have a heat transfer associated with the heat exchange may be zero or non-zero, depending on how the control volume is selected. We're just talking about, kind of where it's going. You see the heat coming in, fluid A, and the control volume boundary. And so then you have the cooling of refrigeration, and you have mass flow rates, right? And because you have the flowing through there. And remember, we use these so that we can have that temperature drop. And in the heat exchanger, the heat transfer depends on the choice of the control volume. Again, we kind of looked at the schematic for that. Pipe and duct flow. The transport of liquids or gases in pipes and ducts is of great importance in many engineering applications. Flow through the pipe or duct usually satisfies the steady flow conditions. Over here for this schematic, heat losses from a hot fluid flowing through an uninsulated pipe or duct to the cooler environment may be very significant. Okay? And then over here, pipe or duct flow may involve more than one form of work at the same time. So we can have different types of work, right? We saw a schematic at the beginning that we had a turbine in there, we had electrical work, we had heat transfer, we had all kinds of different things. So multiple forms of work can occur simultaneously. Electric heating of air in a house. So you see the inlet here, the little coil coming in, going into our boundary, crossing the boundary, and coming out. And then here we have the error involved in the change in H, right, where CP is less than 0.5% for air, is negative 20 to 70 degrees Celsius. So that's the error that is associated with less than 0.5% of air in temperature range. So what this is saying is that you can have an error involved of 0.5%, but the temperature range is significant with the error. So you wouldn't think that with an error so small that it would have that profound of an effect. So many processes of interest involve changes within the control volume with time. Of course, we've been talking all about flow rates and things like that. Such processes are called unsteady flow or transient flow. So remember, we had steady, and that's remaining constant, that's unchanging. And then we have transient, which is unsteady, that is changing, right? And so most unsteady flow processes can be represented reasonably well by the uniform flow process. So if you think of something that's always changing, we are going to try our very best to put it in a little box so that we can calculate and we can go forward with it. And we have been able to do that reasonably well by using the uniform flow process. And so this uniform flow process is the fluid flow at any inlet or exit is uniform and steady. So we have to take our unsteady flow and our ever-changing transient flow and make an assumption. The fluid flow at any inlet or exit is uniform and steady, and thus the fluid properties do not change with time or position over the cross-section of an inlet or exit. If they do, they are averaged and treated as constants for the entire process. That's because when you have things that are always being used, they're just like our refrigerator, we need it to work all the time. Just like the power plants, we need them to work all the time, right? So are you going to go and take all of these measurements and all of these calculations and then find all of the property table dynamics for all of these at every second and then say, oh my gosh, but I could get it at every half a second and then I could get it at every quarter second? It's just never ending. So at some point you have to pick and go forward. And this is what has been shown to work reasonably well. This is a uniform flow process. So here, charging of a rigid tank from a supply line is an unsteady flow process since it involves changes within the control volume. So this is just showing that there's a change within the control volume. Okay, the size and shape of the control volume may change during an unsteady flow process, right? Because so you see we have the control volume and we have that seed boundary, but that can move, right? So the volume and size of the control volume may change during the process. Here's the mass balance equations for those and the energy balance equation for those. And then again, we have more formulas that are up here, but that's not what I want you to focus on. I want you to focus on the theoretical portion of it, knowing what a nozzle is, knowing what a diffuser is, things like that. And then just becoming familiar with these things. You will learn the formulas and how they work in the problem solving examples for one inlet system and one exit systems. And I do want you to take away that there's a lot of formulas to be used, and just knowing when to use them is what's important. And then working those based on questions is, in my opinion, how you get there. The energy equation of a uniform flow system reduces to that of a closed system when all the inlets and exits are closed. So that makes sense, right? We have all of these, things that we can throttle or even just close. And so then when we do that, then we equate it to a closed system. The uniform flow system may involve electrical, shaft, or boundary work all at once. Remember, we just talked about that. You can have a ton of different things happening all at once simultaneously. Charging of a rigid tank by steam. Anytime you see rigid right here, that means you're going to have no boundary work. Your boundary work is not going to exist. It's going to be zero. Anytime you see this, boundary work equals zero. And that's because rigid means that your tank's not moving. Your tank is this. Your boundary's never moving. Nothing is moving. Okay? So you should have a rigid tank, okay? And so you have a mass flow. We have an imaginary piston, but this is what we're talking about here. You see the rigid tank there, and this is the rigid tank on this side. Didn't want you to think that we were talking about this. Okay? And then the temperature of steam rises from 300 degrees Celsius to 456.1 degrees Celsius as it enters a tank as a result of flow energy being converted to internal energy. So just again, the conversion of energy can make the temperature rise. discharge of heated air at a constant temperature. So if we have electrical energy coming in and we need the discharge of the temperature going out, we have those formulas as well. And then in summary, we just talked about the conservation of mass. The conservation of mass is the exact same thing as the first law of thermodynamics, but within a mass, and when we're talking about a process, right? Flow work and the energy of a flowing fluid. So we talked about that. Flow work is just when something's flowing into maybe a controlled volume, right? You have an inlet, you have an outlet, maybe you have two inlets and an outlet, and that flow is doing work, right? And then again, if we take that and incorporate time into it, then we can get rates as well. Energy analysis of a steady flow system. So that's when we start talking about things that we need to flow constantly. The refrigerator, the steam power plant, things like that. Some steady flow engineering devices, that's going to be the turbines, that's going to be the nozzles, the diffusers, the things that we talked about those. And then the engineering analysis of unsteady flow processes. We take those unsteady flow processes and then we assume that some parts of it are steady so that we can calculate it and that those properties are not changing. But then we do know, on the unsteady, maybe we do have and are able to incorporate some of those boundary works, and things like that. And then the introduction of rigid and what that means and how when you have a rigid tank, well, then nothing on that tank is going to be boundary work. And that's it. And we'll see you for the next lecture.